Okay, we'll go ahead and get started. Yeah, so thank you for the invitation. It's really nice. It's really nice timing for me because I'm going to tell you a little bit about Muon G-2 experiment and the physics behind Muon G-2 experiment. And it's actually very recently we came out with our first result on the Muon G-2 experiment just a few weeks ago. So the experiment is at Fermi National Accelerator Lab, which is a lab near Chicago. It's kind of in the suburbs of Chicago. This photo is of the sort of main office building in the lab, at the lab. But the lab itself is a big site, many square miles. And it has this big accelerator complex on the site. And it's that accelerator complex that we use. In the talk, I was going to tell you a little bit about magnetic moments of particles, because that's what we're measuring in the G-2 experiment. I was going to tell you a little bit about these subatomic particles called muons, because that's what we're using in the G-2 experiment. And then I'm going to tell you a little bit about how the experiment works. I'm going to show you 2 videos how the experiment works, and then just see where we are right now. And, if you just stop me with questions, you know, that would be great. I mean, if I'm just answering your questions, that's another great way of doing the talk. So, in the experiment, we are interested in the magnetism of a muon. And an example of the type of magnetism that we're measuring is, for example, the magnetism of a bar magnet that produces a magnetic field, a dipole magnetic field. A lot of atoms are magnetic and produce a dipole magnetic field. And also a lot of elementary particles, all the building blocks of elementary particles that matter is made of. They're magnetic too and produce a dipole magnetic field. So dipole magnetic field is kind of the magnetic building block that's equivalent to electrical charge as an electrical building block of nature. If you just had to get a sort of mental picture of how you get a dipole magnetic field, you could just imagine a point charge particle orbiting in a circle. So that produces a little circular electrical current. And that electrical current of that orbiting charge particle, that produces a magnetic field. And that's a dipole magnetic field. And on this, this is I think the only slide that has some equations on. Not quite, but this little equation here is that relationship between the orbital angular momentum of a particle executing a circular path and the corresponding magnetic moment that characterizes the dipole magnetism of that circling particle. And you see it involves the charge of the particle, because if it wasn't charged, there would be no current, no magnetic field. Involves the mass of the particle. When we write this down, we introduce, the reason I put the formula here is I want to introduce this G, because this G is, it's G-2 experiment. G is very important to us, because we're really measuring G, or actually G-2. If you just had a single particle orbiting in a circle, point-like particle orbiting in a circle, this relationship between the angular momentum of the particle and the magnetic moment that it creates, the G value G would be 1. But that's just for that special case of a point particle going around in a circle. That magnetic moment then determines a lot of things. It determines how the particle interacts magnetically. So for example, it determines the torque that magnetic moment or that particle or that atom or that biomagnet would experience in a magnetic field. So they tend to be orientated in a magnetic field. It determines, can determine the force, magnetic force that magnetic moment will experience. If you place it in a, for example, in a non-uniform field, it will experience a force that pushes it towards higher field. Okay, so this is a very famous experiment that it's interesting because this is an experiment that dates back to the early 1920s, I think. The interpretation of the experiment that we have now is actually quite different from the interpretation Stern and Gerler, who did the experiment, had at the time. So they didn't interpret it in terms of what I'm going to talk about, which is spin, magnetism associated with the spin. But nowadays we understand it reflects that. So the experiment is very simple. There's kind of this oven here on the left that produced a beam of silver atoms. Now the atoms themselves are neutral, so it's neutral particles going through the magnetic field. But the atoms have a magnetism that's associated with the lone unpaired electron, better off pointing over here, there's an odd number of electrons in silver, and there's one unpaired one, and that determines the magnetism of the silver atoms. So those silver atoms are magnetic. They have a magnetic dipole moment. And when they enter this region of non-uniform magnetic field, there was an equation for the force on the magnetic dipole. And so that there is a force on the magnetic dipole, and you would expect, depending on the orientation of the dipole, the silver atoms to be kind of dispersed by the different forces, magnetic forces on the differently orientated magnetic dipoles. In the experiment, what they saw is not just this sort of dispersion of the magnetic silver atoms due to the magnetic forces, but they saw that you got two distinct deflections. So one up deflection and one down deflection. And so that was a sort of really surprising, really an amazing result. So nowadays, the way we interpret it is that there's a new dimension of nature we're seeing. This is one of the first evidence of that new dimension of nature. And that new dimension of nature is intrinsic spin. It's an angular momentum of elementary particles, for example. That's not, and this is an important point, it's not associated with a particle orbiting in a circular motion or some sort of electron top rotating around. So you actually don't want to think of it like that. We don't really know the details of how it comes about, but it's some new dimension of nature that an electron comes with and other elementary particles come with that has an associated angular momentum. We call it spin angular momentum. So this was really a discovery of a new dimension of nature. So that was a really, really important experiment. And with that spin, like we saw for the charged particle within the circle, becomes a magnetism. And actually all these elementary particles of nature, all the ones that make up the matter around us, they all have this spin dimension. And so they're all magnetic, and they all have a magnetic moment. And they were able to measure the magnetic moment of the electron. And this is why I introduced that G. We normally talk of this as kind of the measure of the magnetic moment. It's a dimensionless number, and they found that G equals 2. So it was not G equals 1, like if you had that simple picture of a charged particle going around the circle. Oh, I don't know why I even did that. Okay, so at that point, it's completely, they found this new dimension in nature. They measured the magnetism of the electron, G equals 2, but it's completely unexplained where that's come from and why G equals 2. So the next step in the story was a theoretical step by, you probably heard of Paul Dirac, and probably likely heard of the Dirac equation. So in that, those early 20s of the last century, they were trying to put together relativity and quantum mechanics, to join those two things together, these two new kind of revolutions of the time, join them together into a sort of relativistic quantum mechanics. And Dirac came, they talk about it, you see this, right? It was like this marriage of quantum mechanics and special relativity. And when he joined together those two things, quantum mechanics and special relativity, in this famous equation, is over here, he found this amazing result, right? So in that equation is a wave function. That's the psi. You know the wave function from Schrodinger's equation. And Schrodinger's equation, the wave function depends on position and time. And if you square, you get the probability of finding the particle as a function of position and time. The wave function in the Dirac equation has 4 extra dimensions. And that just came out of joining together relativity, special relativity, and quantum mechanics. And 4 extra degrees of freedom, I should say. And they correspond to this intrinsic spin, this new dimension that was found by Stern and Gerlach. So spin up and spin down. And then matter and antimatter. That's another dimension of nature. So those 4 extra degrees of freedom were that electrons can be electrons or positrons, matter or antimatter, and they can be spin up and spin down. And that all burst out, joining together quantum mechanics and special relativity. Now, I don't know of any sort of wordy explanation why that comes out of that. But it came out of joining together, making consistent special relativity and quantum mechanics. And the other thing that came out of it, which was, this is like the sort of goodie bag at the end of the party or something, was a prediction for the magnetism of an electron. So it actually predicted the value of G, and the value of G that was predicted was 2, which is what Stern-Gerlach measured. And so that was incredibly successful. Okay, so those were the 1920s, and now we're going to roll forward kind of 20 years or so to the late 40s. This is actually the time when quantum field theory got developed, which is sort of a full-blown joining together of special relativity and quantum mechanics. And one of the big impetuses for the development of quantum field theory was what emerged was actually a puzzling result for the electron's G factor, its magnetism. The Stern-Gerlach experiment measured G factor to, some percent level, many percent level precision. But with time, the G factor measurements got more and more and more precise. And they were able to do that by if you take atoms, hot atoms, and we do it with sodium and do a gallium, and you put them in a magnetic field, you see in the spectra of the atoms the effect of the magnetism of the electron. But depending on the orientation of the electron, up or down, you see two states. And so when you put sodium, gallium in a magnetic field, you split states. It's called the Zeeman effect, according to whether the electrons spin up or spin down, whether the electron's magnetism is one or the other orientation. And it's a little more complicated than that, but you can see here what sort of this is a sort of spectrograph of the colors of light that are emitted by sodium. And what this is meant to indicate is that this is a famous pair of lines in sodium. We don't need to worry what they are, but they get split, and they get split in part when you put them in a magnetic field, in part because of the magnetism of the electron. There's also contributions from the magnetism associated with orbital motion, but the important thing for these experiments was the magnetism associated with the electron. And by measuring this splitting very precisely, and this is a famous experiment by Cush and Foley. Cush got a Nobel Prize. They were able to determine the G factor of the electron very, very precisely to, fractions of a tenth of a percent. And at that level, it disappeared to disagree with G equals 2. So this was then like a crack in Dirac's theory for the electron. And it was shortly after that it actually got explained. It got explained within a year by Julian Schwinger, who was a famous theorist, famous with Feynman, with others for the development of quantum field theory. He calculated that there is a small deviation from G minus 2. Sorry, small deviation from G being equals to 2 for the electron, due to, you can think of it, we'll think of it in a moment as the influence of the vacuum, but you can also think of it, the electron kind of interacting with itself. And so in quantum field theory, if I just drew this, actually I've drawn this for Muon, I should have drawn it for the electron. If this is an electron, this is its magnetism represented here. And then there's a little correction to the electron's magnetism that arises from its self-interaction. This is where it's emitting a photon and reabsorbing a photon. And that little correction, Schwinger calculated, it comes out to be a really simple result. It's fine structure constant alpha divided by pi. So fine structure constant is 1 over 137 approximately, divided by pi. And that's exactly the discrepancy that was seen in the Foley Cush experiment. And so that was a huge achievement. It was one of the first big sort of validations of quantum field theory that explained the value of G minus 2 for the electron. So, just to bring that up to date, now that emission and absorption of a photon by the electron is sort of the lowest order of many, many corrections. So what we now recognize is that in quantum field theory, the vacuum, empty space, is not really empty space. It's full of all the sort of particles, electrons, positrons, photons of nature, constantly appearing and disappearing, being created and annihilated. And those particles that are appearing as sort of foam in the vacuum, these particles are appearing and disappearing, affects the magnetism of the electron. and affects the magnetism of all particles. And that's what they were measuring in the Cush-Foley experiment, was sort of the effects of this quantum foam in the vacuum that is predicted and calculated within quantum field theory. And this to me looks like a piece of art, but nowadays that first contribution of the vacuum to the electron's magnetic moment, now that's calculated to many orders, to 10 it's unbelievable really, 10 significant figures. By calculating, hundreds of these different graphs, and I don't know what any of these really mean. I see photons in them, I see electron loops in them, electron-positron loops in it, but those have all been calculated. So the electron's anomalous moment, that G-2 piece, that difference from 2, is calculated to 10 significant figures, measured to 10 significant figures, and verified. So it's one of the most precisely measured things in physics. And I won't go into any details on this. This is the experiment that, more recently has measured that, where they basically trap electrons in a magnetic field, an electric field, and they're able to measure the magnetism of very precisely of individual electrons. Okay, so that's a sort of story of why elementary particles are magnetic, and the magnetism of elementary particles is really quite interesting. So what about muons? So muons were discovered as constituents of cosmic rays in the sort of mid-30s, 1930s. It was actually really the result of a lot of different experiments. But there were two teams, one at Caltech and one at Harvard, that finally claimed the existence of a new particle of nature. But it really built on 2 decades of experiments with cosmic rays. The claim for a new particle was because once they started to measure the mass of the cosmic rays, they found that they were much heavier than electrons. So those particles they knew about it, they weren't electrons, and they were much lighter than protons, another particle they knew about. So it had to be a new particle because there was no other particle known between, the mass, the very light mass of an electron and much heavier mass of a proton. And nowadays, again, it's sort of revisionist history, but now we recognize that discovery of the muon was really the discovery of the second generation of elementary particles. The electron, the up quark, the down quark that make up ordinary matter, everything around us, they're first generation particles. There appears to be 2 further copies of that, the second generation and the third generation. And the discovery of the muon was the discovery of the second generation. It's the first, second generation, non-first generation particle to be discovered. So muons have been used a lot in science and engineering and even in archaeology and homeland security, for all sorts of things, although we still don't know why there are muons. We don't know why there are muons, but we know a lot of the properties of muons, and we put them to use in industry and so forth. But I just got a couple of slides on some of the more physics type uses of muons. So, you all know relativity and some of the sort of dramatic effects like time dilation, length contraction. The first real demonstration of time dilation was made using muons. So muons act like little clocks because a muon, we had a muon on the desktop. Its lifetime is 2.2 microseconds, 2 millionths of a second. So it's like a clock, one clock tick is 2.2 microseconds. and then it goes. And so you can use a muon as a clock. And so if you have muons, cosmic ray muons streaming down, they're like moving clocks. And so you can measure the lifetime of moving clocks. And that is an important, they're moving very close to the speed of light. And the measurement of their time dilation, that they live much longer than 2.2 microseconds, as measured from the rest frame of the Earth, looking at these moving clocks in the cosmic radiation, was an important verification of time dilation. And the only reason we see muons at sea level is because of time dilation. Because it would take them, without time dilation, they would have decayed before they reached sea level. There's actually, if you Google it, there's an interesting, they made a movie. One of the first pair of experimenters made a movie about the time dilation experiment. It's on YouTube. So one of the interesting things about muons is that, as I say, they decay, they're completely unstable. And they decay actually to electrons. So they're kind of partners to electrons. We think of them as a heavy sort of brother or sister of an electron. They have the same charge as an electron. They have same spin as an electron. They have same types of interactions with an electron, electrical and magnetic weak interactions. So that they're heavy partners to electrons. But because they're heavier, they can decay back into electrons. And their decay is quite interesting because their decay is, it's written out here. It's actually an important part of our experiment. The muon decays into an electron by ejecting a neutrino and actually an anti-neutrino. That's what these symbols mean here. And that produces electrons that have this sort of continuous energy distribution. And I'm mentioning this because I'm going to come back to it later. It has this continuous energy distribution. And also this process kind of looks like beta decay, radioactive beta decay. And one of the big early discoveries for muons was that their decay is really just like beta decay and has the same universal strength as beta decay. And so this was important work at the time. This shows a very, this is now 1950s. This is a very famous picture actually. And it's a shows a very famous decay sequence. So when cosmic ray protons hit the upper atmosphere, they actually produce particles called pions. And then it's those particles called pions, which are strongly interacting particles. They then decay to quickly decay to muons. And then the muons then decay to an electron. And so this is what we would call a decay sequence, like, with radioactive isotopes, there's famous decay sequences, uranium decay sequences, all sorts of decay sequences. In particle physics, subatomic physics, it's really one of the most famous decay sequences where you get a pion that decays to a muon, that decays to an electron. And it's a decay sequence that's used at many accelerator labs in the process of working with pions or working with muons, and making beams of pions and muons. There's a very interesting thing about it. And it was observed right at the time that you might have heard of parity violation. Parity violation in weak interactions is a handedness, a left-handedness to the weak interaction. And it was discovered in beta decay of radioactive materials, but it was also almost simultaneously discovered with muons. parity violation, handedness or weak interactions with muons. And the way you actually see it here is so that this pion decays to a muon. Here comes the muon from left to right. The muon has a spin, as we said, it's like an electron, has a spin. And it has a magnetism. And when it decays over here to an electron, for negative muons, those electrons tend to be ejected opposite the spin. And for positive muons, they tend to be emitted in the direction of the spin. There's this huge anisotropy of the electrons being emitted. And that's a signature of this handedness, left-handedness of weak interactions. And so that was discovered really just about the same time as the handedness in beta decay. And I mentioned this one because it's also a key ingredient in the G-2 experiment. Okay, so those are two bits of background I probably talked too long about. One is that all the particles of nature that make up the matter around us, they all have this weird dimension of nature, we call it spin. And they all are magnetic. They all have magnetism. And measuring their magnetism has been a very fruitful thing. And then, you know, from 1936, we found this new particle that's not part of ordinary matter, muon, which is actually a member of the second generation of particles that are not part of ordinary matter. And it's been used in all sorts of ways in physics and science and chemistry and biology and archaeology since then. Now I'm going to get on to muon G-2 experiment. So our goal was to measure very, very precisely what we call the muon anomalies, kind of like what they call the electron anomalies, the difference of the muon's G factor from 2, G-2. Actually, the anomaly strictly is G-2 over 2. So it's that fractional difference from G being 2. And the reason we do it is that it can be measured very, very accurately. And it can also be calculated very, very accurately. And finally, it's sensitive to all the particles that can be appearing and disappearing in the vacuum, whether we know those particles, like electrons and photons, etc., or whether we don't know those particles. So we view the muon's magnetism, or this anomalous bit of the magnetism, as kind of this probe to look into the vacuum and explore the contents of the vacuum. I noticed this slide has got messed up a bit on here. I don't know why this electron, it shouldn't be electron going down like this, hadronic going down like this, and new physics going down like this. But anyway, so this is meant to show you how they actually calculate the anomalous magnetism of the muon, that bit that's different from Dirac's prediction for the magnetism. So there's a piece, it's over here on the left, that comes from the electrons and the photons in the vacuum. And actually that's by far the biggest piece, but it's very, very, very precisely calculated. There's a piece that comes from, so the muon, like an electron and other particles, interact through the weak force. So there's a contribution to the anomalous magnetism of the muon that comes from weak interactions. So weak interactions are the particles associated with weak interactions, neutrinos and what we call W and Z bosons. They're appearing and disappearing in the vacuum. They contribute too. That's a very tiny piece, but it's also a well-calculated piece. And then there's a piece that comes from strongly interacting particles. So you can think of it as coming from up, down, and other quarks in the vacuum, you can think of it as coming from strongly interacting particles like neutrons and protons and pions that are appearing in the vacuum. And that's depicted here in this piece. An example would be the creation of a positive and a negative pion in the vacuum. And now it's an interesting piece because the muon doesn't interact strongly. So it can only see that the strong particles in the vacuum indirectly through the fact that the muon interacts electromagnetically, and the strongly interacting particles also interact electromagnetically. Anyway, this creates a contribution. And this contribution is much smaller than electromagnetism, but it's bigger than the electroweak contribution. And most importantly, it's the least certain in the calculation. And then right over here on the right is the fact that, well, look, this is all the stuff we know about. Every particle we know about, every particle in what they call the standard model is contributing to the magnetism of the muon to some extent or greater or lesser extent. So every particle in the standard model is contributing. Every particle beyond the standard model that we don't know about would also contribute. And so the question is there, if you do this calculation, is there something missing? Are there new forces, new force-carrying particles that would contribute, new particles of matter that would contribute? All sorts of things, new phenomena. This anomalous magnetic moment of the muon was measured. The last precision measurement of it was back in almost 20 years ago now. It's this data point over here. This stands for Brookhaven National Lab. It was another US sort of national laboratory where they measured it. This point over here, this is SM stands for standard model. This is sort of our current theory of particle physics. And that's the calculation based on this picture up here. As you see, for 20 years, there's been this long-standing discrepancy between the best measurement and the theoretical calculation of the muon's magnetism. And for 20 years, there's been this long-standing question about whether this is evidence for new forces or new particles or whatever of nature, or there's something up with the experiment, or there's something up with the calculation. The difference firmed up a little bit over the past 20 years because the calculation got a bit more accurate, and that discrepancy, was standing at 3.7 standard deviations. So in particle physics, there's this sort of standard that you've made a discovery if you've got a 5 standard deviation effect. I don't know, I think that's like 1 in some number of million statistical chance. But of course, it's not quite fair because you're always worried about systematic or a mistake or something like that. So 3.7 sigma is nowhere near that. It's sort of scales of many thousands statistical chance of being 3.7 sigma off. But again, you're more worried about an unknown systematic in an experiment or an unknown systematic in a calculation. But anyways, 5 sigma is the normal standard. So it's not been accepted as a discovery yet. Okay, so long story short, we are remeasuring the anomalous magnetism of the muon. And our goal is to measure the anomalous magnetism to a precision about 4 times better than the Brookhaven National Lab experiment. And that, this year we've had run 4 right now. We're going to have 6 runs over 6 years. And we just published our run 1 result, which had a precision just a little better than the Brookhaven experiment. But anyway, let me show you how the experiment works. Here is a picture of the experiment. So, we want to measure the magnetism of the muon. And so basically the way you measure the magnetism of the muon is you trap muons in a uniform magnetic field. And this is a storage ring here, which we inject muons, and it has a uniform magnetic field. And in that, as they orbit around in that uniform magnetic field, their magnetic moment, their magnetism, well, that's going to experience a torque. And so it's going to precess around as the muons also orbit around. And actually, we watch that precession. And what's neat, one neat trick, I'm going to explain it, about the experiment is we actually watch what's called an anomalous precession. It's the difference between the rotational precession of the muons going around in a circular path and the rotation of the spin as the little muon bar magnets rotate. If G was exactly 2, and I don't think there's any deep explanation for this, but if G was exactly 2, the orbital frequency and the precession frequency of the magnetic moment, they would be exactly the same. And so it's a very nice trick on the experiment that we look at something that's determined by the difference between we're measuring a difference frequency. And so we directly measure G minus 2 rather than having to measure G and subtract off 2, which would be a very painful thing to do. It costs you a factor of 1,000. Okay, so now I want to show you a few videos, I think, a couple of them. I can do it. Okay, this first one shows you the experiment is based on this 50-foot diameter storage ring that has a 1.5 Tesla magnetic field. That's a large magnetic field, and it's a very big magnet. So this stores, I think, 8 megajoules or something of energy. So it's a very big magnetic field with a very large magnetic energy. And so that storage ring is superconducting storage ring. And the coils for the ring, so the bits that actually carry the current, were shipped by barge around Florida from Brookhaven National Lab to Fermi National Lab. It came up the Mississippi River. So there's an outer coil and kind of an inner coil. You might know the magnetic field of if you have a current loop, right? You get magnetic fields that say come through the loop and circle around. If you had 2 coils with currents going in opposite directions, one a little larger, one a little smaller, you could imagine in the middle, you'd have no magnetic field, they cancel out. Outside, you'd have no magnetic field. You get a strong magnetic field between the coils. And so that's the way it's built. And then you put iron, at that region between the 2 coils, and that magnetizes the iron, and you get this really intense magnetic field, 1.5 Tesla. So that's how it's built. So as you watch this video, that's what you're seeing being kind of constructed. As I say, it's 50-foot diameter. And it was an amazing engineering thing we used the same storage ring to dismantle it from Brookhaven National Lab and reassemble it. So this is the iron that is underneath the coil. And now they're building all this structure to bring in the coil and lower the coil. And as I say, it came on a truck, a barge, and then another truck. And they're sliding it in. The red frame is just a frame to stop it, breaking. And now they're going to lower it onto the iron. I think they are, yeah.
So the magnet are the 2 gray rings?
The magnet is the 2 gray rings. And actually you can see that there is the inner one is actually 2 rings. So there's a little technical detail there, but the red has now gone away. So the red was just the frame. Now they got the bottom steel and the coil, and now they're going to load the top steel on. And it's all these little segments. And this happened over a space of about a year to put all this together. So it's like this giant jigsaw puzzle. And that is the magnet. So as I say, it's steel, and then these two, I think of it as two coils, slightly smaller, slightly larger diameter one, and steel again. And that produces the 1.5 Tesla magnetic field. Oh, I got another one. Forgot about that. Okay, now I'm going to show you so inside that magnet, we put a vacuum tube in which we inject the muons inside the magnetic field. And then I'm going to show you here just a sort of muon's eye view of what the muon will see as it orbits around, because there's lots of instrumentation that gets added. I think it's this one. So first there comes simulation of muon going around the experiment. And you're seeing a lot of things here. Maybe I'll stop it for a moment. And maybe I'll play that. Can I do that a little slower? No, I don't know how to do that. As you go around, you're seeing, you see this plate up here, this plate down here, and this plate over on the left and right. That's an electrostatic quadrupole. If you just put a muon in a charged particle in a magnetic field, yeah, it'll go around in a circle. But if it had any momentum upwards or downwards, it would go around in a helix. And so it would either, they spiral out the top or spiral out the bottom. And so to stop them spiraling out the top and the bottom, we need something beyond just the magnetic field. And so we have a electrostatic quadrupoles. Basically, you know, supposing the top and bottom plates are negative, we store positive muons, the negative, positively charged. And if a muon heads up, it's going to be repelled back down. If it heads down, it's going to be repelled back up. So we need these electrostatic quadrupoles to confine the muons within the storage ring, in addition to the magnetic field, which confines them in the circular path. And so you're seeing these quadrupoles. You're also seeing, I wish I could slow this down, but detector systems as we went around. Here's now a real camera inside the ring. So this is real inside the ring. This is a detector system for watching or measuring decay electrons, tracking them. And these are the quadrupoles. You see these plates? And they're arranged all around the ring. About half of the ring is occupied by quadrupoles. Okay, so I want to say a little bit more. Yeah, this is the other place, there's an equation, but it's not much of one. So I wanted to make this point about the concept of the experiment, because we want to measure the anomalous piece of the magnetic moment, this G-2. And the way it's done is, so this, imagine this is a sort of quarter of a turn of the storage ring. Here comes the muon walking its way around. And these blue boxes are actually the detectors that we use to detect the electrons from the muons. So in this first picture, imagine a muon up here, it's traveling horizontally. It's that at that moment, its momentum is towards the right, and its spin vector is orientated towards the right. It moves around the ring in a circular orbit under, the centripetal force. So its momentum direction is changed, and also the spin experiences a torque. That's direction is changed too. If G was 2, those changes will be identical. So this is showing you the effect of G not being 2. And as you go further around the ring, the spin in red and the momentum in black get further and further out of phase. Now, this is greatly exaggerated. In the real case, if the muon goes around the ring 30 times, then the spin has actually rotated 31 times, approximately. So that's the kind of scale of it. It's exaggerated here. Now, just with some basic like 232 physics, you can write down. You probably did this in 232. What we call the cyclotron frequency. It's the rate at which the momentum rotates. And you can also write down what's called the L'Amour frequency. It's the rate at which the spin rotates. And those are these two equations here. So omega c is how fast the momentum is rotating, and of course it depends on the magnetic field. The bigger the magnetic field, the faster it rotates. And this is the sort of rate at which the spin rotates, what they call the L'Amour frequency. And if you look at those two equations, well, if G was 2, this is the really intriguing bit. If G was 2, they'd be exactly the same frequency. And if you can measure an observable that depends on the difference of them, then you can actually measure the difference of G from 2. And that's what we do. We're able to measure the anomalous frequency, the rate at which the spin processes differently from the cyclotron frequency, and that's proportional to this product of the muon anomaly in the magnetic field. So let me show you why we're sensitive to that anomalous frequency. That's the other trick in here. So the basic idea is that I mentioned that the muon decays into an electron and 2 neutrinos. We're going to detect the electron. The electrons, when it's a positive muon, they're actually positrons, tend to be emitted in the direction of the muon spin. So the muon acts kind of like a flashlight. Imagine the spin as the body of the flashlight, the spin vector, and the electrons are going to come out the light end of the flashlight. And so the electrons are really telling you the direction of the spin. Now, if the spin is in the direction of the momentum, when you boost from the rest frame of the muon to the lab frame, where we're measuring the electron energies, the energy of the electron is boosted up when it's emitted in the direction of motion. And if the spin is opposite the direction of the motion, when the electrons get emitted, they're boosted to a lower energy. So you get high energy electrons when the spin is pointing in the direction of the momentum, and you get low energy electrons when the spin is pointing opposite the direction of the momentum. It's kind of like, supposing you were on, it's a relativistic version. If you were on a truck, right, traveling down the road, and you're standing on the back of the truck, you threw the ball forward in the direction the truck's going. The pedestrian on the pavement will see that ball having more kinetic energy, more velocity, than if you were on the truck, it's going from left to right, you throw the ball in the opposite direction to what you're doing. It would have, for the pedestrian there, would see a lower velocity for the ball, a lower kinetic energy for the ball. And that's exactly the way the experiment works. So what we do is, I did have, I think, I wonder if I got an animation of that. No, I don't. There's one I forgot to carry over. So we measure in those detectors, we measure the number of high energy electrons. And the high energy electrons kind of oscillates up and down as the muon spin rotates about the momentum vector. And so we directly see the anomalous precession that way. And this plot here shows the measured time distribution of high energy electrons. So it decays away because the muons are decaying. And this is 10 lifetimes of the muon wrapped round and round again in this histogram. So it wasn't really like a really long, thin histogram. We wrapped it around. And so it's decaying, the muons are decaying away, but their energy is going up and down and up and down and up and down as they are pointing in the direction of motion, opposite direction of motion, in the direction of motion, opposite direction of motion. So you get this wiggle. The black are the data. And then the red is our fit, basically of a decay curve with sinusoidal wiggle to that data. It's a little more complicated than that, but from that fit, we extract the frequency, the anomalous frequency. And if we know the magnetic field, we can calculate the anomalous magnetic moment. So we have to know the magnetic field. I won't go into the details of measuring the magnetic field, but it is measured extraordinarily precisely. We have hundreds of NMR probes. I don't know if you know that. NMR probes are devices you can use to measure magnetic fields. You measure a frequency. So around that 50-foot diameter ring are hundreds of these probes. But they're outside the volume that the muons are in, because otherwise they would, would impede the motion of the muons. We then have a little rail car, a trolley. We park it in a garage, and we turn the beam on, and it comes out of the garage, and it travels around the ring. There's a circumference of the ring, and it's got probes mounted on it. Got an array of probes on it. So it measures a three-dimensional map of the magnetic field in the storage room. And from a combination of those two things, so the probes that are outside the storage ring are constantly running. So we'll measure any fluctuations in the magnetic field at the time. And then the trolley system will measure the magnetic field within the ring, where the muons are, but at certain times. And by combining those, you can determine your magnetic field very accurately. Okay, so we had this moment in the experiment. Am I getting onto that? Yeah. We did the experiment in an interesting way. So the two big groups in the experiment. One measures the magnetic field, and the other group measures the muon precession frequency. So the team here was measuring the muon precession frequency, and when we measured the muon precession frequency, we were actually blinded to the result. So we spent 3 years analyzing the data, but we could not tell what the frequency is. The frequency we measured in clock ticks, but the meaning of a clock tick, the size of the clock tick, whether it's 1.25000000 nanoseconds, was kept secret from us. So there were 2 scientists outside the experiment that had sealed envelopes with the actual size of the clock tick. So we did our analysis, 3 years of analysis, figuring out the anomalous precession frequency of clock tick. And then finally we had this meeting where it's called the unblinding meeting, where the envelopes that are open, the size of a clock tick is extracted, and suddenly you know your result. And so obviously at this meeting, we all had to agree that whatever comes out of the envelope, we're going to publish that result, right? We wanted to be blind to it. And so I got a little video here. It's pretty short. This is when they open the envelope. So one of these is a little subtlety, but one of these numbers is a clock frequency. And so these are the two envelopes for that clock frequency. And then they quickly put that clock frequency into a spreadsheet, and you know your result. So let me explain this graph. So this was a spreadsheet that was set up before the meeting. On it is, over here on the left, is the theoretical prediction. Upstairs here, this was the Brookhaven measurement. And so that is that 3.7 sigma discrepancy. And then when we got the clock tick frequency, it plugged it into the spreadsheet, and then this number appears. This is the Fermilab experiment result. And then this in magenta here, this is just the average of the two. They're consistent, and so we can average the two. And so it's at that moment where you suddenly got the result of the experiment, that first run of the experiment. And so that discrepancy then became, the combined result is now 4.2 sigma. Now that's our first run. We're actually collecting 20 times the data of the first run, approximately 20 times the data of the first run. And so we think of that first run as, really confirming this Brookhaven result. We had all new detector systems, all new analysis, all new electronics and everything. I mean, we used the same storage ring, but we really confirmed the Brookhaven result and have increased the significance of the Brookhaven result. But it also drives us to keep working and keep measuring, because we're still not at, a 5.0 sigma kind of discovery threshold. But of course, this was a really important result. I can show you how things get can get exaggerated in the press. So this is BBC World News.
Working on a project in the United States, saying that they have discovered strong evidence for the existence of a new force in nature. They say that some subatomic particles, or muons, don't behave the way predicted by current theories of physics. The British funders of research say that scientists are on the precipice of a new era of physics. Our science correspondent, has a story. The theories of modern physics have given scientists...
Well, I won't go into all the rest of it. But anyway, that's where we stand right now. We are analyzing, and UK is involved in, has a big component of analysis in the run 2 and 3 analysis. That will give us a result that has about 4 times the data of run 1, so should have twice the statistical precision. And then overall, when we get to run 6, with the continuous sort of improvements in the experiment, we should reach about 20 times the data, about 4 times the statistical precision. Okay. Maybe I'll finish there. Thank you.
Any questions? Can I ask a negative question?
Mm-hmm.
What if somebody hit the storage ring with a hammer, like before Brookhaven got started, and there's some crack somewhere that we don't know about? Is this the type of thing that down the road the data would tell us, or is that the type of thing that would be a system?
Yeah, so that's a very interesting question. So what are the differences and what are the similarities between the two experiments? So all the detector systems, all the analysis, all the electronics, everything outside the ring is completely new technology. The storage ring, actually the storage ring, the magnetic field was 10 times better in the Fermilab experiment, 10 times more precise, because although that basic ion and coil, that's the same. But what I didn't tell the story of is what we call the magnetic shimming. So to get that very uniform field, you have to do what they call shimming the magnetic field. They have different levels of basically moving in or out pieces of magnetic material iron to make a uniform magnetic field. So a very coarse version of it. You saw all those big segments of steel, right? You can tighten bolts or loosen bolts to, adjust the positions of the steel. But in the Fermilab, and they get in this smaller and smaller adjustment. In the Fermilab experiment, we had 10 times smaller adjustment, where they actually took mylar sheet. They put aluminium coatings on mylar sheet to make the finest shims. And they could do that because they were able to collect data that they couldn't collect in Brookhaven. 20 years later, 25 years later, there's all this internet, technology for, we have these little trucks that will go around the ring and measure the magnetic fields and produce these maps really carefully. And then they would automatically print out these sheets of, these shimming sheets, basically, to improve the magnetic field. So the magnetic, although the basic ingredients of the coil and the big metal, big iron is the same, the actual magnetic field is really 10 times better. We of course measure the, in both experiments, the magnetic field is measured where it counts. So, and in both experiments, still not perfectly. But, I think it would be surprising to have the same, therefore, to have the same problem leaking to both. Yes.
Just how prevalent are muons compared to like our plastic particles that electrons, like you said, they don't last like an AD.
Yeah. So I think you're asking like at any instant, how many muons are there around compared to the numbers, say, of electrons? And I would treat that as zero. Because they are streaming. I can give you some numbers, right? 1 square meter at sea level, where we are right now, there's 100 muons streaming through that square, every square meter. So that sounds like a big number, there's hundreds going through you. But compared to the number of electrons we can made up of, it's of course completely nothing.
So how are you tracking it, I guess?
Oh, I didn't. I didn't.
Maybe I missed it.
I didn't really. Okay, so I thought I got one out. I better cut out a lot of stuff. So but it's not a Fermilab just because there was a building there. We're using the accelerated complex to create a beam. Nice. And we made it with that decay scheme that I described. Yeah. So we take, just like cosmic ray muons. Protons hit the top of the atmosphere, they make pions. Pions decay, they make muons, and then they decay to electrons. At Fermilab, they make a beam of protons. They hit a target, they make pions. They decay to muons, and they get injected into the storage room and see the electrons. Yeah. So it's really that copy of what happens naturally, but at an accelerator. And therefore you can make many more muons with the accelerator.
Thank you so much, Dr. Gorringe.
Yeah, thank you. Thank you for the invitation. As I said, I was really happy with the timing of this one. Because I've given so many talks where there is no result.
So because the statistics have been done once, and the new data runs come in, is it a much easier process Or do you have to start from scratch?
No, you build on what you thought from the previous layer. What will be the challenge, probably, one challenge